We now know where the neuronal projections from higher brain areas synapse in the spinal cord, and we know the pathways that they activate through these synapses. But where in the world are these high-level neurons? Much of what we know about the root of motor control in the cerebral cortex goes back to the studies of Wilder Penfield, a Canadian neurosurgeon who lived throughout the 20th century. Penfield lived at the time when doctors were beginning to operate on epileptic patients, removing the parts of their brain responsible for causing seizures. He got permission from his epileptic patients, who were kept awake during the surgery, to use an electrode to experimentally stimulate different parts of the cerebral cortex, to map out what stimulations produced which sorts of behavior. Penfield found that stimulating a particular area of the cerebral cortex, just anterior to a deep fold called the central sulcus, could cause marked muscle twitches in his patients, even when the stimulations were very weak. The muscle twitches consistently occurred on the side of the body contralateral, opposite to his stimulating electrode. The area that Penfield localized is now known to be the primary area for controlling voluntary motor movement. It's known as primary motor cortex, M1, or Brodmann area 4. Neurons with their cell bodies in M1 project directly to lower motor neurons in the spinal cord and brainstem, where they tell these neurons, and subsequently the muscles that the neurons innervate, what to do. This is how voluntary control of muscles, at its simplest level, works. Commands from M1 travel through the dorsolateral path into the spinal cord and synapse onto alpha motor neurons and interneurons to guide motor activity. Because they originate far above the lower motor neurons in the spinal cord, cells projecting out of M1 are known as upper motor neurons. M1, like most cerebral cortex, has 6 distinct layers, and the classic upper motor neurons arise from layer 5 and are pyramidal in shape. These are the upper motor neurons most tightly coupled to muscle movement. However, other neurons in the cortex are also involved in voluntary movement. On the anterior side of M1, for example, lies the so-called premotor cortex, or Brodmann area 6. Penfield found that stimulating the premotor cortex could also generate motor movements. However, while stimulating particular areas of M1 resulted in highly specific muscle movements, stimulations in premotor cortex caused complex multi-muscle movements, such as the rotation of an entire limb. Thus, the premotor cortex appears to be involved in higher-level motor behavior than M1, perhaps encoding specific patterns of motor output that can be selectively engaged, based on situational demands through activation of particular neurons in M1. Another higher-level motor area is the so-called posterior parietal cortex, or Brodmann area 7, which lies posterior to M1 towards the occipital lobe. The posterior parietal cortex has been shown to be essential in planning movements, taking into account the location of the body in space, as well as the location of various other objects with which the body might need to interact. The presence of areas such as the premotor cortex and the posterior parietal cortex demonstrates that, like in the visual and auditory processing streams, there is an entire network of cortical neurons responsible for sending motor commands of varying levels of complexity. As in the visual and auditory systems, however, most of what is known about cortical motor system involves the simplest level of processing. So we'll focus our attention here on the primary motor cortex, M1. Neurons in M1 appear to be involved in the initiation of voluntary movements. Making a movement in a particular direction is preceded by the firing of a particular subset of neurons in M1. So does making a particular series of sequential movements. When, for instance, we play the piano, specific subsets of upper motor neurons activate in a particular sequential manner. Wilder Penfield also discovered just how the upper motor neurons are organized in M1. He found that if he stimulated one part of M1, he could reliably cause twitches in the hand. Stimulating another part, he could elicit movement in the tongue. Another part, movement in the hip, and so on. Penfield used his studies of epileptic patients to map out the body parts that upper motor neurons in various parts of M1 correspond to, and he found that, like in sensory cortex, the neurons of M1 are organized in a somatotopic map, with specific regions responsible for innervating specific body parts. Penfield coined this topographic representation of body parts in M1 a homunculus, the Latin word for little man. As in the somatosensory cortex, the various parts of the body are not evenly represented throughout M1. Specifically, body parts involved in the most complex motor behaviors take up the most real estate in M1. You can see this overrepresentation of certain areas on Penfield's homunculus. Notice how the face, with its over 40 individual muscles, is disproportionately dominant. With an especially large portion of M1 dedicated to the lips and tongue in humans, given their critical role in producing speech. The hand, and the thumb in particular, is also especially exaggerated on the homunculus, which makes sense when you consider how many fine motor movements it must carry out.